Having discussed the definition of axial loading and the material response, let's discuss about normal stress and displacement due to axial loading. And one thing I have to tell you is that in undergraduate solid mechanics, we're gonna focus mostly on this elastic regime. If we start to consider this ductile and beyond the yield point, the analysis on stress and strain and deformation becomes much more complex. So yeah, please understand that and have in mind that we're gonna focus on this elastic regime where we can describe the relationship between stress and strain using one proportionality constant called Young's modulus. Okay, so let's try to obtain the relationship between force and displacement for our the cylinder under axial loading. So the cross-sectional area is A, the length is L. Then suppose that this is subjected to tension force P, and after this tension force, the length becomes L plus delta, and delta is the displacement. So if you focus on the material property, sigma equals to be E times epsilon. To use material property, you need normalized stress and normalized strain, normalized displacement. Okay, so normalized displacement strain is defined as sigma over E, and this normalized force sigma can be represented as P over A. This is normalized stress over cross-sectional area. Now, after adding this normalized force, you have to also add normalized displacement definition in the strain and put this into here. So then what you have to do is, then what you're going to see is, delta over L equals to be P over A over E. And what you can realize is delta must be PL over A, PL over AE. Okay, so this is the relationship between displacement delta and force P, and this is somewhat intuitive. So when you have large cross-section area, you're not gonna have large displacement. When you have large Young's modulus, which means that large Young's modulus means is stiffer material, you're gonna have similar displacement. When you have larger force, you're gonna have larger displacement. When you have longer lengths, you're gonna have larger displacement. Yeah, because like when you have really small length L given the same force, you're gonna have a similar deformation. Okay, so these are the answers that we can get out of this simple material property relationship, sigma and epsilon relationship, and normalized force and normalized displacement. And I think some of you may have seen this expression back in freshman physics 2. Okay, so this is the relationship between displacement and force represented by material property Young's modulus and geometrical information, length and area. So using these kind of simple analysis, what you can do is you can try to draw free body diagram and try to predict the displacement. So one kind of example problem that I can suggest to you is this typical problem. When you have like a rigid wall here, you have a pillar, but the pillar does not have the same cross-section. It has large cross-section A1 in the beginning, but after some point it becomes smaller cross-section A2, and there is 3 forces acting on F1, F2, and F3, and the original length is L1 and L2. Okay, so the information for this problem is the external forces and material property, which is Young's modulus, and geometrical parameter like A1, L1, A2, and L2. And this problem asks us how to obtain the displacement delta. Okay, so to obtain this solution, what you have to do is, of course, divide and conquer strategy. You have to divide the structure into simple and smaller structure, and given imaginary cut and given imaginary subsection, you have to draw free body diagram and try to predict the deformation within specific region. Okay, so what you can do is following. So you have to first make an imaginary cut here. Whether you make an imaginary cut here or there, if your imaginary cut remains within this range, you can draw free body diagram like this. F3 is the external force, N3 is the reaction at this imaginary cut. Okay, and to make a mechanical equilibrium, N3 must be F3, and F3 is given as 120 kilonewton. Yeah, kilonewton, as I told you in previous lectures. Now, if you make a imaginary cut here or there, whatever imaginary cut you are making within this zone, yeah, you're gonna have these kind of free body diagram. You're gonna have two external force, F2 and F3, and you're gonna have like a one reaction at that imaginary cut. Okay, so after considering the mechanical equilibrium, N2 must be negative 60 kilonewton, or it's under compression. Now, if you consider, let's see, imaginary cut here and there, wherever point you make an imaginary cut within this zone, this is the free body diagram you're gonna see. Okay, whether you make a cut here, the N1 will be same. After considering the mechanical equilibrium, N1 will turns out to be 240 kilonewton. Okay, so after making divide and conquer strategy, yeah, you can make this section and that section and that section. For these three sections, you have within this zone you're gonna have N3. Within this zone you're gonna have N1. Within this zone you're gonna have N2 force, and within this zone you're gonna have N3 force as a reaction to F1, F2, F3. Then after obtaining this N as a function of a position, you can see like you have like a three value, N3 120, N2 negative 60, N1 240. Then you can see that there is tension, compression, tension, and the length of this zone is L1 over 2. Length of this zone is L1 over 2. Length of this zone is L2. So you plug in like L1 over 2, L1 over 2, and L2 here. For each zone, you obtain delta 1 equals to be force, length, cross-section area A1, material property. For area zone 2, this zone, you have N2, which is negative 60. You have length, which is L1 over 2. This is L1 over 2, and you have cross-sectional area A1. You have material property E, and for third zone, you have N3, and you have total length of N and L2, and you have cross-sectional area A2 and material property E. And after considering the deformation in zone 1, zone 2, and zone 3, summing up all the deformation, you can obtain total deformation delta. Okay, so this is how you approach the problem when the structure seems complex and when there are many external forces. What you have to do is you have to use divide and conquer strategy. Of course, I'm very experienced, and whenever I see this problem, I immediately see where I should make an imaginary cut to solve this problem really easily. If you don't have this practice back in freshman physics years, then please do this practice by yourself. You have sample problems and you have homework problems, and you can do these practice by yourself and until you get used to draw free body diagram. Drawing free body diagram is the basis for learning solid mechanics and dynamics and all those solid related discipline in mechanical engineering. So please get used to draw free body diagram for your future as a mechanical engineer. Now let's solve another example problem. Now we have the cylinder 2, but this cylinder has interesting geometry. This is a solid cylinder except this is space. You have a hollow cylindrical hole here. You have a solid cylinder outside. Okay, so and here the external force is only acting at one point F. Okay, and the question is obtaining the displacement. And the geometry is given as L1 here and L2 here. Now in this problem, what you can do is you can make an imaginary cut. Wherever imaginary cut you are making within this zone, what you're gonna see is for any imaginary cut, you're gonna have the same cross-sectional area. You're gonna have the same reaction force. Okay, so you can consider this entire body as a whole section 2. You can consider this this imaginary cut as whole section 1, and you can draw free body diagram for each. body in the right will have free body diagram like this. Body in the left will have a free body diagram like this. And for each body, you have length L1, you have length L2, and you have cross-sectional area. For this guy, area will be D2 over 2 square pi r square. For here, the area will be D2 over 2 square pi minus D1 over 2 pi square pi. Okay, so it will be area 1 here. Okay, so the area, this is your area 1. This is your area 2. The diameter is D2, diameter is D2, and inside is D1. Okay, so after identifying a length and cross-sectional area and the force, then what you can do is the total displacement must be delta 1 plus delta 2, and you simply plug in force times length divided by modulus and cross-sectional area, and it will give you the answer. Okay, so whatever complex axial loading problem you're gonna have, the essence and the basic of solving and approaching the mechanics problem is to draw free body diagram. Okay, so please try to draw free body diagram correctly, and once you draw free body diagram, you will be able to apply the force displacement relationship quite easily, and that will be the end of solving and approaching axial loading problems. Okay, this is the simplest kind of and simplest type of the problem, and that's why it's the first chapter out of 4 reactions. Okay.